Yeah, so hi everyone, I'm Luca, and I'm going to talk about Gluon-W, which is a cryptocurrency stablecoin protocol. Um, yep. So just to start off, I just want to acknowledge the people that were involved with writing the paper. So the first is Bruno, who came up with the idea of Gluon. Um, then there's Mohammed Shahir, who did the formal verification, and he was a student at Carnegie Mellon University in Qatar. And then Giselle Reese, which was his supervisor. So it's the outline for the talk. So I'll just go over the different types of stablecoins, how Gluon works, uh, the main theorems, and then certain issues that we found while we were working on it, and then uh, future directions to solve those problems. So just basically, there's three main types of stablecoins so far. There's asset-backed, so like the big ones, USDC, Tether. Uh, they hold you have to trust them to hold a physical reserve. Um, then there's crypto-collateralized, like DAI. So you put in collateral, and then the stablecoin you get is like effectively a loan, but the collateral you put can get liquidated if the price depegs, and that's like out of your control. And then there's crypto backed like JED, Gluon, and Dexy, and that just requires that the algorithm is properly implemented, and that in the case of UTXO, the off-chain executors don't stop working, so people can still interact with the protocol. So just a review of how Gluon works. There's four main actions that as a user you can do. Um, so fission is the act of putting in your base coins. So in the case of Ergo, it would be putting in Erg, and that'll spit out the stable coin, so the neutrons, and the reserve coin, which we call protons. Uh, then there's fusion, which does the opposite. So you put in the neutrons and protons, and you'll get your Erg back minus a fee. And then there's beta decay reactions. So beta plus can convert your stable coin to a reserve coin, and beta decay minus can convert the reserve coin to a stable coin. And you pay a fee for these actions. Um, and then we just define so from the reserve ratio, um, which tells you it's like the factor by which the reserves are greater than your liabilities. You can define the fusion ratio, which is just the fraction of the reserves that backs the stable coins. And from that, we can derive like the stable coin price and the reserve coin price. And then, yeah, so I want to go into how these equations work, but basically, uh, when you do beta decay reactions, the protocol keeps track of the cumulative volume of the reactions over a certain time, t, and the fee you pay is based on this difference. Yeah. So the first important theorem is we want to make sure that the peg gets maintained. That doesn't so the price doesn't diverge, right? So when we're in the peg state, so the stablecoin price in that equation that I showed before, it equals the oracle price. We show that the price you pay is bounded within a certain limit. Um, and in order to derive some like meaningful equation for the case of the theorem, we just make some assumptions to make the calculations easier. So that the volume of your reaction isn't large, for example. And uh, when we mean like the price of buying a stable coin, so at the beginning I showed the reactions of fission, but that gives you protons and neutrons. So to just get neutrons at the end, you want to do a beta decay plus, where you'll take those protons from the fission and then convert them to neutrons. So then at the end, you only have stable coins. And it's a similar process for the other way around. So for selling, um, when you want to sell, you'll just have stable coins. So you're gonna have to convert some of them to protons and then do a fusion. And again, when in the case when the price is the peg is maintained, so the neutron price equals the oracle price, then yeah, the selling price is bounded by this effective fee. So this effective fee is so it takes into account the the two actions of doing a partial beta decay and then a fusion. So yeah, so just an aside. So in the case of buying neutrons, we also have this effective fee, which is like represents the cumulative fee for doing a fission and then a beta decay. With the given equations for the actions that we have in this protocol, it's pretty complicated to derive like a value for this effective fee. So that's why in the current implementation, if you go on the Gluon.Gold website, we don't do cumulative actions. Like you can only do each individual one for simplicity. In order to if we wanted to implement that to make it easier or more like to improve the UX, you'd have to derive it ends up being a polynomial equation for the effective fee because the beta decay fee depends on this effective fee as well. So you end up getting a polynomial, and deriving the coefficients for this polynomial is a lot of algebra. Then you have to write an algorithm to compute the coefficients based on like how many stablecoins the user wants, then find the roots, and then the root is the value of the effective fee, and for that you can solve for m, which is how much erg they'd have to provide. And it's the same process for buying just one if you just want to buy protons, but it's a different equation, but it's the same process. And with selling neutrons, there's a slight difference because we have to because remember I mentioned that we have to convert some of the stable coins uh, to reserve coins and then do a fusion. So we have this like I call it the gamma factor, and that represents the amount of your initial amount of stable coins that you have to convert to protons. And so par- in so in this case, our polynomial is about finding this value of gamma. And then once you find it, you can figure out what the effective fee is, and then uh, how much erg you can get if you want to sell and stable coins. And yeah, the process is similar for selling just protons. So a cool thing about Gluon is that it's resilient to price crashes up to a certain amount, and that's what this theorem wants to show. And it's similar to the jet theorem. Uh, it's actually the same equation, except where there's a Q star, it was Q and jet. Um, uh, yeah, so, and by the price crashing, we mean the oracle price. So if the oracle price goes down by some amount, then we can show that the neutron price, as we defined it earlier, won't change. And then another nice property is that the equity of the bank is always positive. So that's you don't want that to be negative. And the equity is the part of the reserves which, um, as a proton holder, you have a right to. So if you just hold stable coins, you have a right to the total reserve amount minus the equity. And we show this theorem shows that basically the proton price always increases, assuming the price remains pegged, except in the case when you want to do a beta minus. So converting stablecoins to protons when the reactor is depegged. Yeah, so and I'll also explain why that happens later. So this is good as a proton. So it's like an incentive for holding protons because you know as if the bank stays pegged, if the price stays pegged, then uh like the price of your protons will go up. Um, so as we were trying to prove the theorems, we had to make some initial assumptions to make our derivations easier. And one of those was this lemma, which said that the absolute value of the ch change in volume was less than the reserve amount. Um, and if we assume this, then we could make some like simplifying assumptions. Uh, However, I wasn't able to find a straightforward proof of why it was true. And like I tried, but I wasn't satisfied with what we had come up with. And yeah, eventually I found a counterexample. It's kind of funny, which is you basically um, start off with some amount of protons, and then you, s- so you also assume that uh, like we're using real numbers, so you can like divide them infinitely and so on. Uh, and then you just divide by two, and then convert those protons to neutrons. Um, and then you'll have a leftover amount of protons, and then divide that by two and convert that to neutrons, and then do that over and over again infinitely. And then you can see that the volume of the reaction actually ends up exceeding the reserve amount for appropriate val for if you use like the correct values of the variables in the equation at the bottom. Yeah, so this meant this lemma was false. Um, but luckily, in the first and second theorems, we don't actually end up using it. Um, yeah, and this is a theorem that was true in JED, but isn't in the case of gluon because you can always mint more protons. So your share of the equity can decrease since more protons can um, get into circulation. Whereas in JED, the amount that got minted was bounded by a certain amount. Uh, this would be a nice theorem if it was true. Like it would be a nice property to have. But in the case of gluon, it's not. So it is possible for a bank run to happen because when so as I mentioned before, to sell your stable coins, it's like the you're combining two actions, right? You're doing a partial decay, beta decay, and then a fusion. But that beta decay fee depends on the volume. So the more people sell, the higher this fee will be. And so the next person will have to pay more. So they're incentivized to sell as early as possible. However, because this fee increases so much, at a certain point, the fee is so high that it's pointless to sell. So you can wait that amount T, which is a protocol property, and then wait for the fee to go down again, and then you could sell at that point. Um, and this is another important theorem which we would have liked to be true, but was unfortunately false, is the no reserve drainage. Um, so basically, this says that, so ideally you would want, because of the fees you pay, the total value of the assets you have before an action should be greater or equal to the total value after. So, and by value, we mean the amount of base coins you have. So, for example, ERG plus the amount of stable coins you have times the price. So those, so why that product is because those units match the units of base coins. So it's like represents like the volume of stable coins you have in units of, in our example, ERG, and then the same for protons. So you want this value to be greater than the amount after the action. However, there's this funny thing that happens when the state is depegged. In the case of beta plus and beta minus, if this like a difference in the case of beta plus if it's positive, then this won't be true. So what that means is that you could uh, you could sell your protons, but then the proton price increases, which doesn't make sense. And so all of these problems that I mentioned, they're related to the fact that before in the beginning of the presentation, I showed the equation for the fusion ratio. It was the minimum of this parameter Q star and this ratio. And this ratio is what we call like the reserve ratio. So the reserve divided by uh, the oracle price times the number of a circulating supply of stablecoins. But then we take this value and then obtain a what we call a normalized reserve ratio, so that when it's above the cutoff ratio or R star, um, it's just equal to the reserve ratio. So the in this plot, it's like the straight line. Um, but then once it's below, so in the deep state, we do a min function so that it just becomes this constant number and hence the flat line. So because we define it this way, this flat line causes all of these problems. So how could we fix the issues? Well, first is instead of using a constant function uh, for the normalized reserve ratio when the reactor depegs, we use a linear function um, so that it goes to the initial value is 1 and it just decreases smoothly. Um, and we could make this single modification to the current version of Gluon-W while keeping everything else the same. But we could also improve the volume equation to make it easier to calculate in the smart contracts, and because it's easier to implement. And even though we can derive equations for the effective fee, in order to avoid these complicated calculations, we could just restrict the amount of volume that's allowed uh, for a given transaction, and this will make composing reactions easier, and so we'll be able to improve the UX. Yeah, and that's it. Yeah, so T itself is it's like a protocol parameter. So you define that ahead of time before launching the stablecoin. So in the case of Gluon Gold, it's 14 days. So in if I go back to the volume calculation. So um, what I'm trying to, so let's say you do a beta decay reaction now. You want to calculate the cumulative volume of reactions in the interval between now and now minus t. Yeah. 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 So So with respect to theorem one, theorem two, the point of those theorems is also to show that it's you, you assuming everything with the blockchain works properly, it's always more cost effective to purchase and sell stablecoins from the reactor itself than from a secondary market on a DEX. So you're always going to end up paying more if like there's a liquidity pool on Ergo DEX with Ergo and Gluon Gold, right? It'll be cheaper to buy directly from the reactor instead. Yeah. Yeah, so current in the current like if on the website because we have implemented the only the actions separately, you'd have to okay like calculate the fraction. You'd have to convert to protons to then do a fusion to get back your erg minus phi. Uh, so it's not like the most so the UX is not that great, but that's like the process effectively. You can always redeem back your base coins minus a fee. Um, so I'm a bit confused. Yeah. Uh, I haven't checked honestly. Yeah. Uh, but the website says how like if you go on Gluon.gold, you can see how large the reserve is. I think there's like 10K or yeah, a little over 10K erg inside the reserves. Yeah, so let's say you do a fission, right? You'll have stable coins and protons. So if you just hold protons, um, if the price of erg goes up, then the price of your protons increases. So you can get more erg. You can then sell your protons and get more erg from the reserve. And so I can explain why. So um, if the price of so in the equation for Q, you can see the oracle price. If the price of erg goes up, then the uh, oracle price goes up, right? And Q will increase. Uh, oh wait, No, that's wrong. Um, oh, sorry, no, I'm confused myself. Sorry. Well, no, 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 polynomial, not differential. Polynomial.